Okay, let's move on to mixer. Well, this is a Gilbert style mixer, very typical design. Bottom, you have a current source, you have an input jam, and depending on the headroom, sometimes the current source is not there, right? You can have just the input connected to ground, having just a simple common source stage here, and you have a fully switching stage and the load stage. And one of the homework problem was to figure out what the gain is, and you know how to find it now. Now, if you look at this mixer, well, you're receiving this signal that is amplified from the LNA. So signal level is bigger, but LNA also has a gain that looks like a common source stage like this. So its linearity depends on the VGS minus VT of this device plus inductance. So, but for the mixer case, you have just a GM, then you are receiving the amplified signal from the LNA, then you may need to have more input dynamic range to receive the larger signal, amplified signal from LNA. So sometimes you put the resistance here and here. Let me try to draw it. Yeah, sometimes you put resistance here, then your input range is increased at the cost of reducing the effective GM. But you don't distort the signal, so you need to be aware of that. And the other thing is how about the LO switching part? Do I want to have a full switching, meaning that I want to have a LO signal that is large so that you have a plus minus one type of gain, or partial switching means there's smaller signal swing. I think in the previous lecture I mentioned that this is the preferred way because if you have a smaller LO swing and if this quad transistors, 4 transistors are not completely switching to plus minus one, then you may have a 0.9, point, and the other side 0.1, 0.1, 0.9, like that, right? Well, if the temperature doesn't change, then this is okay. But if temperature changes, this value also changes too, because the overdrive VGS minus VT, that level changes. So the gain of this switching pair can be temperature sensitive. Therefore, it is better to have a fully switching if you want to have a kind of gain insensitive temperature insensitive gain on this switching transistors. Okay. Okay, this is a passive mixer. Basically, you go to the active mixer, and if you take these four transistors and put them like sideways, and then input and outputs are like this, then this is passive mixer. And A and B nodes can be terminated with the voltage mode amplifier or current mode. So either you connect this way or you connect this way. Either depending on there are two different modes that you can select. We'll talk about more when we talk about the frequency translated impedance. And here, what you need to know is that the again here the linearity versus gain noise figure trade-off is there, meaning that passive mixer is quite linear compared to the active mixer. However, because it is a passive passive component, there's no bias current, there's no amplification. Therefore, gain and noise figure is worse. Therefore, if you want to use a passive mixer, the LNA has to work harder to amplify, and the mixer does not, because the passive mixer does not amplify signal. So we need to be aware of that and make a trade-off there. And also, we'll talk later, but LO can be either 50% or 25% duty cycle, and 25% duty cycle is often used these days. Although initially people used the 50% uh, uh, duty cycle LO, but later they switched to 25% duty cycle because this potentially has a higher gain that you can achieve. We'll talk about that in later slide. Yeah, here I already yeah, this is the slide that talks about that. So why 25%? Well, first let me tell you about what the 25% clock means. 25% clock means duty cycle means is waveform like this. This is the L clock waveform, and the 50% means the generated clock, the full phase clocks is 50 supposed to be 50%, but here you only see 25%, right? And this has an advantage over 50% duty cycle case when it's when it is current driven. First thing is that this LNA goes to I mixer and Q mixer. And if you have this 25% duty cycle, the LNA current either goes to I or Q, only one at a time. If you have a 50%, they're always connected to I and Q. So current, there's some division, but if you have a 25% duty cycle, only one of the mixer is connected to the LNA output. So 100% RF current goes to the mixer. And if you do the calculation, you'll see that, well, because of that also, there's a 3 dB higher gain. And if you can achieve the higher gain, that means lower noise, right? If you compare these two cases, 25% duty cycle versus 50% duty cycle. Yeah, and this is kind of the repeating what the first bullet says. Switches in IQ mixers are on at the time. And the because you have a higher gain in the front, if you use TIA, transimpedance amplifier, which I showed you earlier, right, like this. And if the switching passive mixer is there, if it's a current driven, the mixer current will flow through these resistors, right? And because you have a higher gain in the front, the TIA noise will, if you refer to the input, will have a less contribution. Therefore, you can achieve a low noise figure. And if you look at this paper here, they did a lot of analysis on this. And also another good reference, I put it here. You can read these papers. They have a very thorough analysis on these. Okay. There are many blocks I'd like to talk about, but I cannot spend too much time in each building block. So I'm showing you some references so you can go deeper, so that you can go deeper if you're interested. And each block, you can easily take a whole course to talk about it. Okay, so regarding mixer, what needs to be checked? Well, gain, all those 25% duty cycle, 50% duty cycle, people have already analyzed it. But a practical consideration that you need to be aware of is always a lot of matching related issues. Especially we know that I and Q path needs to have a 90 degrees, and then I and Q path needs to have a good gain, right? Gain matching and differential matching for the IP2, good IP2 and things like that. And although we are making IQ calibration digitally and then doing some correction there, but digital, for the digital to correct, the analog side matching needs to be within the correction range. Otherwise, digital has to put more engine there, right? So we have to, on the analog side, we have to do everything that we can do. So what that means is that transistor on resistance, junction capacitance, gate capacitance, all have to be very good, need to match. and also but this is not that easy to do, right? Because transistors are small, especially at high frequencies, and we like to use the minimum channel length. Sometimes if you just rely on transistor matching, you cannot get what you like to get. So in some case, instead of just using a transistors, you put a series resistance to it, because usually this is a poly resistor, right? And it has a much bigger dimension than the transistor. So resistor, and also resistor is a very simple component, so it has a much better component matching than the transistor. And therefore, if you do this, you lose you have some um, um, you know you lose something. For example, if you have driving with a current, then there's a large voltage swing at the input, and that can be a problem. But at least matching wise, is better, right? Because on resistance is the combination of this poly resistance plus the switch resistance, and poly resistance match well between components, between different among with the adjacent resistors. So that's one of the trade-off you can make. And the other one is the mixture has this is a passive network, and this metal that you have to worry about. I think we talked about it this in previous lecture. And between A and B, which one is a better layout? If it is a low frequency analog circuit, we'd like to do maybe some common sense trade or something. But here this is a gigahertz signal. Maybe simpler layout is better. And also all these lines, we should use a non-minimum metal width, because I know that if you increase the metal width, then it also increases parasitic, but metal resistance also matters if depending on what the value is, because sometimes these metal lines resistance can at lower level it can be like 0.1 ohm per square approximately. So if you have let's say 10 micron and let's say 0.1 micron width, that's about 100 squares times 10, that's 10 ohm, and that plus the LO driver resistance, those things all add up, and they can if they don't match well, your LO phase can also change, and because of the RC time constant. So those are the things we need to worry about, especially at high frequency.